like to do a kind of formal discussion. And okay, so I worked a lot in the context of geomorphometry from a geostatistical perspective. So from the beginning, I tried to analyze what generally is referred as surface roughness with a geostatistical approach, and essentially using spatial variability indices, like, for example, the vector analysis is a quite huge corp, a huge set of references that are very old, from I think from the 80s, from very old from the perspective of research, not from the geological point of view for sure. But and one of the key features of the application of geostatistical indexes for surface texture analysis is that this kind of approach, sorry, because this was not, I need to close the door of my son because he's laughing. Just a moment. Scusa, Leo. Fai silenzio un attimo. One of the good characteristic of geostatistical-based approach is that they permit a directional and multi-scale description of surface roughness. In this case, you can see the application, the calculation of variogram maps for different search window, moving search window. Here we are in a scree slope in the Dolomites. So in this portion here, you see debris flow deposits. Here you have a very smooth scree slope, and here you have an incision, a channel incision. So changing from this place, and this place, the variogram surface of surface morphology, or the trend surface morphology, is very different, both in terms of the spatial variability at different lag distances, as well as in terms of anisotropy. Anisotropy is a very distinctive characteristic of surface morphology. The point is that the directional and multi-scale analysis of surface roughness or surface texture, I use the two terms in the same way, can provide a lot of information on related surface processes, and can be really useful, for example, as input feature, I don't know, in, for example, in landslide susceptibility models, because you can see that in area in which you have erosional processes or depositional processes, many times you have elongated features in the direction of flow lines. And these differences also in anisotropy is very important also when you are modeling, for example, flow processes. The problem is that geostatistical-based approach based on variogram or covariogram are not robust statistics, because are very sensitive to nonstationarity in spatial variability. For example, when you have a sharp transition, like in this case, between the rocky outcrops here and the scree slope here, when you compute a metric in which the search window is in a portion in the scree slope, in another portion in the rocky outcrop, the statistics is very sensitive to the presence of spatial non-stationarity. Then you can also have inside the data different kind of hotspots that can be real, like boulders on the scree slope, or can be an error, for example, bad filtering of vegetation, and so on. For this reason, I moved from a classical geostatistical estimator based on variogram to another quite simple approach. Instead of considering the variogram, that is the half of mean squared differences between points separated by a given distance, I just consider the median of absolute differences. And here you can see the impact of omnidirectional roughness calculation here for this kind of morphology. Here you see on the right the residual DTM, so is the trended, we remove the effect of slope. Here you can see the roughness, omnidirectional roughness calculated for a lag of 2 pixels. So we are considering variability in elevation, in residual elevation, comparing pixel at a distance of 2 pixels. Here you can see the index computed with the square root of the variogram, the modogram, that is just the, instead of considering the squared differences, you are considering the absolute differences. Here you have computed the roughness with the standard deviation of residual DTM. And here you have the MED, the proposed index. You can see that the impact, for example, of hotspot here that are essentially unfiltered trees in this case is just is filtered out. And also the transition, when you have a sharp transition, like in this case from the channel here and the ridge where you have the debris flow deposit, the description of surface roughness is sharper respect to the other. Okay, the point is that my classic approach was a classic approach in geostatistics, that in order to analyze surface roughness, you need the trend, the original digital elevation model, removing a smooth representation of it in order to derive the residual DN, or if you want, topographic positional index is more or less the same concept. The great problem is that you can derive a different version of residual DN in relation to different levels of smoothing. And so when you need to compute roughness related indexes, you have a lot of issues in selecting which degree of smoothness or which approach to smooth the residual DM you need to adopt for calculating roughness. And for this reason, there are other approaches like roughness based on vector dispersion that try to filter out the effect of slope just from an algorithm perspective. But as we have shown, and as also Vincent can confirm, unfortunately, also this kind of roughness measure is in some way dependent to slope. So for this reason, we developed with Peter, also with Peter Gut and Giordano Tezza, an index of roughness that is based on a geostatistical approach that does not require the trending, because we use what is called in geostatistic increments of order k. So in this case, we consider, instead of calculating the spatial continuity index considering differences between pixels, we consider differences of differences. So it is more or less like order 2 derivative. In this way, you automatically filter out a planar trend. In this case, you see on the left a residual DTM and the isotropic roughness index computed for a lag of 2 pixels, computed with the classical approach based on the trending. And here, the new index, the new simplified approach, is applied directly to the DEM without the trending, and you obtain a result that is very, very, very similar to the original one. But in this case, the user has very few options to consider, because it's just to consider essentially the it needs just to consider the radius or the shape of the search window. You don't need to decide the level of the trending. It's all automatic. This new index permits to derive, like the classical one, not only an isotropic or omnidirectional index of spatial variability, but you can also compute index of anisotropy strength and anisotropy direction. And clearly, having these two kinds of information can then combine it to other more complex analysis. Here is just a comparison between the computation of an omnidirectional roughness index for a lag distance of 1 pixel, computed with the new approach directly from the EM. In this central column, you see the new proposed index, and here you see instead the roughness computed with normal vector dispersion. And you can see that in some condition, the performance of the two methods are quite different. For example, with vector dispersion, you have a tendency to enhance ridges and valleys, for example. And you can see maybe here another impact. Here on the left, you have the application of the new proposed index, and here the application of vector dispersion-based roughness. And you can see that where you have a sharp change in morphology, like in this scarp here, but look also here in this scarp along the river bed, yeah, you can see that vector dispersion-based roughness highlight the change in slope above here and below here. Instead, with this index, you describe the roughness on the scarps and not the roughness of the change of slope at the top and the bottom of the scarps. So the information is what we are trying to get in this case, at least in my case. Okay. And okay, this approach is just a kind of prototype, because the same idea could be applied to more complex spatial variability indexes, and also more complex roughness related indexes can be applied. The software is available as a R package, and it's is written in Arial language. You can find the link in Zenodo. I know that I don't know if Peter, did you implemented it also in Microdam, but I think that you implemented the new version of the ruggedness index of Riley, if I'm not wrong. So in conclusion of this, I hope to be able to explain the main characteristic of this approach is that apart from this algorithm, and I think that in relation to roughness analysis, there is the need to define a consensus in the terminology and definition of roughness, because effectively in earth sciences there are very different ways of naming roughness related indexes, and also in different software the same index can be implemented differently, and some indexes have clear issues or clear dependencies, for example with slope, like the ruggedness index, or like the vector-based roughness. And so I think that the community should talk about also the terminology to understand what we mean with roughness, to understand if it is better to talk about surface texture and see roughness as our are a component of surface texture related to short distances, short range spatial variability. In this context, in these days, I'm working in trying to propose a European cost action exactly on these topics. So both related to the concept of roughness in earth sciences, but above all in relation to algorithms and the connection that we have between surface roughness analysis in earth science, in ecological sciences, and other disciplines like surface metrology, image analysis, and so on. In regard to image analysis, this kind of approach are not too much different to the Aralic approach on grayscale co-occurrence matrix, for example. And there are also connections with other approaches adopted in pattern analysis, like, for example, local binary pattern. And here we can also see connection with geomorphons, for example. I think that there are a lot of connection with other methodologies. One of the things that took me to deal with geostatistics, first because I started my career in geostatistics, but because these kind of indexes are easy to understand, and it is easy to connect these indexes with the processes that we are studying. I think that I was more or less able to say everything that I wanted to say. I don't know if Peter, that wrote with me the paper, has some suggestion or comments. Maybe I forgot something.
No, I think the only thing I will add is that Microdam implemented one of the algorithms, and I'm not sure it's the one he's emphasizing here, but a derivative one, which is what we think is correctly working for arcsecond DEMs. Because we've been doing a lot of work with the global 1 second DEMs, and there are real issues with most of the implementations for dealing with that.
It's true, because effectively the algorithm that was implemented in R using the Terra package, it works essentially with projected DMs, and it can work with images, because we just treat the elevation as an image. Here, this approach can be adapted also, like did for a version of it in for geographical coordinates. And you could also work on point clouds, but you need to develop different algorithms. But the concept is always the same.
Sebastiano, could you stop sharing the screen so we can like see each other? Yeah, cool. Wow. Look at that orange desktop.
You're muted, Sebastiano.
Yeah.
Okay, I hope that my presentation of the fly was sufficiently clear. And yeah, otherwise we will do another. And
I think
like it.
yeah, I think it was great. Thanks for stepping up like this. And I'm sorry for the issues. I looked, and like it seems like the email went to everyone but you. So I don't know what happened there. So it's problematic. But yeah, I mean, we can. Hannes is not there either, and he's the one who puts the schedule together. So we can talk with him and see if you do another one in the future, or but I think it was great, and it's recorded, so we share it with our membership. So yeah, I think you did a great job. It was clear, and I really liked it.
I hope to didn't say stupid things, because when I do things on the fly, you never know what come out from my mouth. So yeah.
I think it was perfect. I mean, it was really great.
So do we have any questions from the audience for Sebastiano and his work?
Yeah, also comments, things that you don't like or things that you would like to do differently. For me, if you are interested in also in this idea of the cost action related to surface texture, surface roughness analysis, for sure, I'm here.
Yeah, may I ask a question? Thank you, Sebastiano, and thank you for this for this talk. And actually, I think roughness is, in my view, roughness actually is a scale-dependent concept for not only the definition but also for the computation. And I think maybe I missed some key information in your talk, but I noticed there is words not very familiar with me. It's about bivariate roughness index. I'm not quite familiar with this term. Could you explain it a little bit for me? Thank you.
Excuse me, could you repeat the last part of the question, because I didn't understood I didn't understand the main the final part of the question about the terminology.
Yes.
You were working about multiscale, that the roughness is a multiscale parameter, okay? But then
no, I think I heard a term, or I view a term in your talk is about bivariate roughness index, or bivariate connectivity, or something else.
Okay, yeah, okay.
For the
Bivariate.
Yeah.
No, in the sense that all the basics geostatistical indexes, like the variogram, the modogram, the MED that I'm using, are all bivariate spatial continuity indexes, because you are comparing two values of elevation that are separated by a given distance. In theory, you can also compute, for example, multi-point geostatistical indexes that instead compare two locations, it can compare a set of locations.
Mm-hmm.
And so you can build much more complex spatial variabilities indexes. And in turn, you can build much more complex roughness indexes. And there are people working in multi-point geostatistics that in fact apply multi-point geostatistics for describing complex spatial patterns. The problem is that more complex is the index, more easily you jump in condition on non-stationarity from the spatial statistical perspective. For this reason, it's a good, sometimes a good solution to don't increase too much the complexity of the index. For example, a characteristic of the variogram and also of MED is that it is a symmetrical index. It tells you the variability along a direction. If you compute the index in a direction, north, south, east, west, or whatever you want. But in theory, you can also build a non-symmetrical index that take into consideration the variability in one direction respect to the other. What I mean, for example, ripple morphology is not symmetrical because you have one side of the slope that is very long with a quite gentle slope, and then you have the scarp that is very steep. And so you could also devise indexes that are capable to catch this asymmetry in spatial variability along the direction. But you can build everything. But you are moving from a geostatistical perspective more to an image analysis perspective, I think. I know. I'm not sure that I replied to your question.
Okay, I'll try to search some more information about about that term. Anyway, thank you.
You were mentioned. Did you were meaning bivariate? It's
Yeah.
fine. Yeah. Okay.
Yeah. Okay. Thank you.
Thanks, Quinn. Do we have other comments or questions?
Yeah. Sebastiano, when you show us these images, you always had this very short range distance for your indexes, like 2 pixels, things like that. Did you compare that with larger scales, like larger windows?
Okay. The problem of scale is a little bit tricky with geostatistics because you have 3 different ways in which you can in some way change the scale of analysis, because you can change the lag distances that you are considering. You can change the resolution of the input DM or the smoothing, or you can also enlarge the radius of the search window. And all these factors at the end change what you are calculating. With the new index, given that you have not many choices, because also the lag distance with the new index is generally no more than 2 pixels, because if you consider longer distances, an increment of order 2, so differences of differences, is no more enough to filter out the trend, because when you consider a longer distance, the trend is no more a plane, but likely is a parabola or a more complex surface. So you should consider increment of order 3, 4, and so on, but you start to put in, I think, error inside. So with this new index, the approach for multi-scale analysis and for analyzing the spatial variability at long distances is to change the resolution of input them. Like the presentation that we submitted for the Geomorphometry conference, is just this approach. We compute the indexes using them at different resolution. Indeed, in that case, we used for deriving the different resolution just aggregation by means of averaging, but clearly other smoothing approach can be adopted. It depends. The point is that with the mean, you know what you are doing. When you start to use a more complex kernel, it's different. It's difficult to understand the real spatial support represented in the pixel, because with the average, you know that you are studying the average elevation in a pixel of a given site. When you start to use, I don't know, Gaussian kernel, you really don't know which is the spatial support, because you give more weight to neighboring pixel and less weight to the one that are far. So now no more the pixel is representative of the average elevation that pixel, but is probably a smaller area in some way. So you have, you can compute probably, but it's more complex to. Okay, I like simple things, but I'm open to any approach. I don't know if I gave the answer that you were. Okay.
And talking about implementation, you use the Terra package for R, and is it like a simple implementation? Is it something that I would easily could like
it's very
create something for grass or?
Yeah. First, I have to say that I started to implement this stuff in ArcGIS using Python and the spatial analyst focal function. And it essentially is all a matter of convolutions. So it's very easy because you have windows with weights. I should see the difficult thing is to derive the weights because for computing the differences, because my approach for calculating the weights in different direction, I use bilinear interpolation to correct for the different leg distances that you have in the north-south direction and east-west direction respect to the diagonals. If you don't correct, like in the ruggedness index, you have a bias measure of roughness because you are putting together distance of one pixel, for example, in north, south, east, west direction, and 1 pixel for the square root of 2 in the diagonals. And so along the diagonals, you have tendentially higher variability because the pixels are farther away than in. And so one of the tricky point was to devise this kind of approach that the same kernel in one shot calculate the bilinear interpolation for deriving in every possible direction that you are considering the value of elevation at exactly the distance that you want. 1 pixel, 2 pixel, 4 pixels, 8 pixel, and so on. And then you compute the differences. And from there, you can compute everything. So first step, you compute directional differences, and then you compute the metric. If you want to compute the variogram, you will use the mean. If you want to compute the med, you use the median. But that's it, just focal statistics. And on the multi-scale, the classic approach based on the trending can calculate the roughness for many different
Nice, thanks. Really cool.
If you
Yeah.
want to for the cross testing, I'm here, and in the Zenodov link, we uploaded also all the test file, so you can really check the algorithm and just you do differences, and if it's 0 or a very small number, all is working, I think.
Nice.
Yeah, I can confirm. I tried it in R on some of my data and it worked really well. And then I tried with very big data set and it worked very well too. So it's easy to take and implement on your own data.
Yeah, because Vincent, I saw that also in your group. Did you develop a R package for multi-scale analysis? And
yeah, and we came up with also yet another way of measuring ruggedity, roughness. That is, as you mentioned, you know, most of the measures are correlated with slope. So we came up with a new one that is decoupled from slope. And then we compared with a few existing, but by the time we submitted for publication, your paper wasn't published yet, so we couldn't compare them. But my guess is that they'll perform similarly in terms of not being correlated with slopes, and that's pretty good.
yeah, I think Vincent, one of the problem with the correlation between slope and roughness, apart from the algorithmic correlation, is that on one hand, many times where you have steep slope, you have higher roughness, and so is a natural correlation. But the other aspect is that an apparent roughness, the one that we are analyzing, because we are analyzing a projection of the true surface on a horizontal plane. And so also this could induce a higher roughness with steeper slope. But at the end, I think this is the elevation model.
Yeah, well, it's what I've been finding out is that depending on the scale at which you look at the landscape, it's not always true, for example, that higher slopes have higher roughness, especially underwater. When we start looking at continental slopes that are over a huge area, you can have a steep slope, but what's on the slope is flat. And that's a misconception that we often see, an assumption that we often see. When you look at the fine scale, very fine scale, that's often true. You know, you're going to get higher slope, higher roughness. But when you start looking at a much broader scale, that doesn't always translate.
Yeah, I agree. I was saying, Jenna, if you have flat irons morphology, you have a very steep slope, but the strata are really smooth. And so, yeah, I agree.
All right. Do we have other questions or comments? Good. Well, Sebastiano, once again, so I'm really sorry for the technical issues. I don't know what happened regarding emails, but I'm really glad that you were able to step up on the spot and give us a nice talk. And I hope we'll see you. You're gonna be in Romania, you said, right?
Yeah.
Great.
I will arrive on, I think, Sunday afternoon. So I will be there at least up to Thursday early afternoon for sure. But not sure to be there also on Friday, but yeah, it will be a possibility to talk directly with people.
Yeah, it's gonna be great to catch up in person. So thanks again, and have a good day, everyone.
See you in Esri.
All right, guys.
Bye-bye.
Thanks.